Bismillahirrahmanirrahim. So dear students, I hope you all are fine. So today we'll discuss about the reactions of alcohols and phenols. So the alcohols are very versatile compounds. Why we are saying them as versatile? Because they can both act as a nucleophile as well as electrophile. So you may be curious that how a alcohol can act as a nucleophile, and when an alcohol will act as an electrophile. The simple thing you can keep in mind is that whenever you break the bond between oxygen and hydrogen, the alcohol will act as a nucleophile, right? And when the bond between carbon and oxygen is broken, then alcohol will act as a electrophile, right? The just key you should know in your mind when you have to decide whether alcohol will act as a nucleophile or electrophile. The bond of OH and CO is what decides. So for example, when we have to discuss about when alcohols will act as nucleophile, right? So suppose there is an alcohol, right? Here oxygen with two unpaired electrons, with two lone pair of electrons, right? So what happens is that this oxygen, suppose it attacks on carbon, right? And this carbon is electronically deficient, right? So oxygen is attacking on a carbon. Since oxygen is attacking on a carbon, so this is electronically rich attacking group. So any electronically rich attacking group is called a nucleophile. So here alcohol is acting as a nucleophile, right? What happens next is that since alcohol is forming three bonds, one with R, one with carbon, and one with this OH. So oxygen is having three bonds, and because of three bonds, oxygen is having a positive charge here, right? So because of this positive charge here, the oxygen is becoming unstable, so this H will leave, right? So what we have done is that we have broken the bond of oxygen and hydrogen here, right? So in the previous slide I mentioned you that whenever the bond between oxygen and hydrogen is broken, then in that case alcohol will act as a nucleophile, right? So here alcohol has acted as a nucleophile because we have broken the bond between oxygen and hydrogen. Now second case is when alcohols will act as an electrophile, right? For example, for that purpose, what we do is that we react this alcohol with a proton, right? What happens that oxygen will pick this proton, right? So here the oxygen is acting now as a base. So the difference between nucleophile and electrophile is that a nucleophile always attacks on any electronically deficient center. That can be oxygen, that can be nitrogen, that can be carbon. The condition is that the carbon or the atom on which oxygen is attacking, that should be electronically deficient, right? So electronically rich attacking group is called a nucleophile. But whenever any atom or group of atoms picks a proton, right, it's not attacking, that's just picking up a proton. So whenever any species picks up a proton, that species is called a base. So in this specific case, this alcohol is acting as a base. So alcohol, after picking up the proton, that forms oxygen with positive charge here. What happens now that we have a group that's electronically rich which attacks this carbon. Suppose we have a bromine here, and the bromine is having negative charge, right? So bromine having negative charge, that's strong nucleophile. This nucleophile will attack on this carbon, right? And this OH2 positive group will leave. It will leave as water, right? So important thing now you should note that in the previous case here, alcohol was attacking, but in this case alcohol is being attacked by this bromine, right? So in this specific case, so the alcohol is acting as an electrophile. This is electronically deficient species, right? So since this alcohol is acting as electronically deficient species, this is called an electrophile. and in this specific case the alcohol was acting as a nucleophile because it was attacking on the diffusion center. Right? What important is that now we have broken the bond between carbon and oxygen here, right? So as mentioned in the previous slide, if you have to decide if alcohol has acted as a nucleophile or as an electrophile, the key point is just see which bond has been broken. So if that's the oxygen and hydrogen bond has been broken, it means that alcohol has acted as a nucleophile. But if the bond between carbon and oxygen has been broken, it means that alcohol is acting as an electrophile here. Okay, now we will start with different reactions. So firstly, we will discuss about the reactions that involve the cleavage of OH bond. Cleavage of OH bond, right? It means that we are considering the reactions of phenols as nucleophile, right? So we will compare here the acidity and reactions of alcohols and phenols both. So firstly, we will consider about the reactions with metal. So whenever we have an alcohol and react with metal, what happens that this metal will pick up a proton from here. So we have broken the bond between oxygen and hydrogen here, right? So we have oxygen with a negative charge and sodium with a positive charge here, right? Again, sodium is a spectator ion, so sodium will not take part in the reaction, it will just present in the reaction medium as such, right? So we have an alkoxide ion here. This is negatively charged and it's electronically rich, right? Similarly, you can say we have tertiary butyl group, right? So this is a tertiary alcohol because this carbon to which OH is attached is further attached with 3 carbons here, right? So when we react this tertiary butyl alcohol with aluminum, what happens that aluminum picks up the proton here and it forms aluminium tributoxide, that's salt basically, and we get 3 molecules of hydrogen. Similarly, we have hydrogen here, right? So if you want to predict that which of these will be stronger acid, that this alkyl group, this alcohol, since it is primary alcohol, that will be more acidic as compared to this tertiary alcohol. Now we have phenol, right? So again we are reacting phenol with sodium, right? So we'll have sodium phenoxide here with hydrogen molecule that will be more, right? So since phenol convert into phenoxide and phenoxide is much more stable as compared to phenol, right? So we say that phenols are more acidic because phenoxide ion is produced more, right? So phenols react much more fastly as compared to these alcohols, and among alcohols you can say the primary alcohols react faster as compared to tertiary alcohols because tertiary alcohols are less acidic. The next thing that's important is the esterification reaction. Alcohols and phenols react with carboxylic acids or carboxylic acid chlorides or carboxylic acid anhydrides. Okay, whenever an alcohol react with carboxylic acid chloride, carboxylic acid anhydride, similarly whenever a phenol reacts with these, they form ester, right? So the general formula for ester is this one. So we have a carbonyl group here, oxygen here, we have an R group here, and we have an OR here, right? So if this group is R group, then that will be alcohol, ester derived from alcohol, whereas if this group is phenol, right, then in that case the ester will be from phenol, right? So in general reaction, whenever we have an alcohol, right, so R stands for that's an alcohol, AR means aromatic, right, or we have a phenol. In both cases, whenever we react with carboxylic acid, then reaction is reversible and we get an ester with production of water, right? And when we react alcohol or phenol with acid anhydride. So basically this is acid anhydride. Again, reaction is reversible, and we get an ester with carboxylic acid. So this is the difference in these two reactions. In case when we react the alcohol with carboxylic acid, we get ester with water. However, when we react this alcohol or phenol with carboxylic acid anhydride, reaction is again reversible, but what we get is that an ester with carboxylic acid. And whenever we react an alcohol or phenol with carboxylic acid halide, the reaction takes place in presence of pyridine. Previous two reactions were taking place in presence of an acid, while in case if you react the alcohol or phenol with carboxylic acid chloride, we have to make use of pyridine. That's base, right? So what's the purpose of this pyridine? Pyridine will neutralize this HCl, which will be produced during the reaction. So the reaction is not reversible, right? So whenever you react carboxylic acid with alcohol or phenol, reaction is reversible, water is produced as side product. Whenever you use alcohols with or phenols with carboxylic acid anhydride, reaction is again reversible, and you get carboxylic acid as side product, right? And whenever we make use of carboxylic acid chloride with alcohol and phenol, so the base we use is pyridine, right? And this pyridine, the purpose of this pyridine is to neutralize this HCl that's produced in the reaction, and this reaction is not reversible. Okay, so now next reaction, this reaction will elaborate further. Esterification, or reaction of carboxylic acid and carboxylic acid anhydride, that's carried out in presence of acid as a catalyst, as mentioned earlier, and the catalyst we use is concentrated sulfuric acid, right? So important thing is that the water is formed as a side product here. So the water that's produced side product, it is essential to remove that water as soon as it formed, because if we do not remove this water, the reaction becomes reversible, right? So what's the concept of using concentrated sulfuric acid is that water, as soon as it is produced, sulfuric acid converts that water into hydronium ion, H3O positive, right? So sulfuric acid converts this water into H3O positive, so water does not remain water, it becomes H3O positive. We cannot make the reaction reverse, right? So this is the concept, this is the purpose of using concentrated sulfuric acid. If you do not use concentrated sulfuric acid, the reaction will go reverse. However, when we make use of reaction of acid chloride, we have to make use of base, which is pyridine, right? So as mentioned earlier, the purpose of pyridine is to neutralize HCl, right? So if we do not use this HCl, we do not use this pyridine, so HCl will cause the reaction to reverse, right? So in order to make the reaction irreversible, we make use of this pyridine as base. Okay, so we have esterification here, and suppose we have a phenol or alcohol, suppose, and we are reacting it with an acid chloride, acid anhydride. Right, this is an acid anhydride. So suppose that we have this alcohol and we have to convert that into acid. What we do is that we react with this acid anhydride, right? So we get an ester here, right? So when we introduce an acetyl group in alcohol or phenol, this is called acetylation. So what's an acetyl group? Acetyl group is simply CH3 that's attached with a carbonyl group here, right? So this group, carbonyl group with attached methyl, this is called acetyl group, right? So this is CH3C double bond O, right? So introduction of this acetyl group into alcohol and phenols, this is called acetylation. So for example, we have here salicylic acid. So salicylic acid has a benzene group, also it has a carboxylic acid group and an OH group. What we do is that we react this OH group with this anhydride, So by this reaction, we make use of acid as a catalyst here. So what we get is that we have an acetyl group attached to this OH. So we have carried out the acetylation, right? So you can convert the alcohol or phenol into ester functionality either by making use of carboxylic acid, or you can react these alcohol or phenols with carboxylic acid chloride, or you may react with carboxylic acid anhydride. Okay. So now we will consider the reactions that will involve the cleavage of carbon-oxygen bond, right? So if you remember when I said that whenever you break a carbon-oxygen bond, it means alcohol is acting as a electrophile, right? Similarly will be the case with phenols. However, phenol only act as electrophile when they react with zinc. Otherwise, this reaction is not given by phenols. Right? This is the difference in reactivity of alcohols and phenols, that alcohols can act as electrophile, but phenols do not act as electrophile. So phenols only undergo such type of reactions when they react with zinc. Otherwise, this reaction does not take place with phenols. Right. Firstly, we will consider the reaction with hydrogen halides. Right, so for example, we have HCl, HBr, HI, etc. Right, so alcohols, whenever they react with these hydrogen halides, they form alkyl halide. Right, the overall reaction is the replacement of this OH group with a halogen. Right, so this is alcohol group, and we react with the hydrogen halide here. We have converted this alcohol into alkyl halide plus water is produced. Right. So this reaction is very important. This reaction is important because we can differentiate between primary alcohol, secondary alcohol, and tertiary alcohol by this reaction. What we do is that the primary alcohol, secondary alcohol, or tertiary alcohol, right, they are suppose taken in 3 different test tubes. We add zinc, chloride, and HCl in all of these test tubes, right? So in presence of zinc chloride and HCl, the alcohols are converted into their alkyl halides. So the tertiary alkyl halides react rapidly under these reaction conditions, right? So once a alkyl halide is formed, the reaction becomes turbid. Okay, so in case of tertiary alkyl halide, turbidity is produced immediately, while in case of secondary, it takes some time for turbidity to develop. While primary alcohols do not produce turbidity at room temperature, you have to heat the reaction, right? So if we have 3 different alcohols, primary, secondary, and tertiary, and you have to confirm which one of these is tertiary, just add the Lucas reagent, right? Add concentrated HCl and add zinc chloride, and see which of these produce turbidity almost immediately, right? So the alcohol that will produce turbidity almost immediately, that will be tertiary alcohol, and the alcohol which do not produce turbidity at room temperature will be primary alcohol. So this is Lucas test, and it's very important. You should know about that. Okay, another reaction in which we break the carbon-oxygen bond is the dehydration. D means removal, hydration means water. So whenever you remove water from a molecule, the reaction is called dehydration, right? What happens is that alcohol undergo removal of water to form alkenes, and the reaction takes place in presence of concentrated protic acids like concentrated sulfuric acid, concentrated phosphoric acid, etc. Or you may also make use of catalysts such as anhydrous zinc chloride or anhydrous alumina. Right, so it's important that the catalyst which you are using should not have water, because we are going to remove water from the reaction medium as well. Right, so this is the general reaction. We have an alcohol here, and we add a strong concentrated acid, or we make use of catalyst and heat this medium under these conditions. So we have removal of water, so hydrogen from here and hydroxy from here, that will be lost, and we'll get a carbon-carbon double bond. We'll get an alkene from alcohol. So in the previous reactions, we converted alcohols into alkyl halide, and this reaction, so we have converted alcohols into alkenes, right? So if we have ethanol, simply, right, that's the primary alcohol, right? The primary alcohol undergo dehydration when we heat it with concentrated sulfuric acid at 443 Kelvin. Right, so we have to give higher temperature for primary alcohols, because primary alcohols do not undergo dehydration very easily. It takes time and it takes high temperature, while secondary and tertiary alcohols can be dehydrated very easily, right? So in case of secondary alcohols, what we use 85% phosphoric acid, and we have decreased the temperature. So previously, if you consider that in case of ethanol, we have used temperature 443 Kelvin, but in case of this alcohol, this is 2-propanol, secondary alcohol, we have decreased the temperature to 440, right? So the product will be double. This will be formation of carbon-carbon double bond by loss of hydroxy from this carbon and hydrogen from that carbon. So you can also remove hydrogen from this carbon as well, but since molecule is symmetrical, it doesn't matter whichever hydrogen you may remove. You may remove hydrogen from here, or you may remove hydrogen from here, that doesn't matter at all. In case of tertiary alcohols, what we do, we have a carbon here, so we will remove a proton from here and hydroxy from here, so we will get a double bond like this one, right? So just compare the conditions. We use 100% sulfuric acid in case of primary alcohols. In case of secondary alcohol, we have decreased the temperature and we have made use of 85% phosphoric acid. Now we have decreased the temperature further, 358 Kelvin, and now we are using only 20% phosphoric acid, right? So the ease of dehydration is that you may see clearly the tertiary alcohols undergo dehydration very rapidly, secondary come next, and primary it becomes very difficult for them to undergo dehydration. Right, so in general, what is the mechanism for dehydration is that, so in case of dehydration, as mentioned earlier, that we make use of some acid as a catalyst. So what is an acid? Any species that can donate a proton, right? So acid donates a proton. So this is a proton which was donated by an acid. So alcohols will firstly, what they do, they'll pick up the proton. So here alcohol is acting as a base, right? So we have this protonated species, oxygen with positive charge here. So in the next step, this oxygen in the form of water will leave, right? And why it's leaving? Because oxygen is having a positive charge. So oxygen with positive charge is not stable, right? So this bond will break. So if you can see that we have broken the bond between carbon and oxygen. So here the carbon will develop positive charge. So now our alcohol has become electronically deficient. This is an electrophile. So in the last step, what we do is that proton from the next carbon, this proton will be lost. Right? This proton will give up its electron, and here we will develop a carbon-carbon double bond, and this proton will be lost. So we have a carbon-carbon double bond here, and the proton has been lost. So by the end of this reaction, we have recovered the proton again. So in the previous reaction, the first step was this proton was picked up by this alcohol, right? And by the end, this proton has recovered. Right, so any species that is used up during the reaction, that participates in the reaction, speeds up the reaction, and is recovered unchanged by the end of reaction, such species is called a catalyst. So this H positive is acting as a catalyst here. So this is the mechanism of dehydration. Okay, the next is oxidation, right? So oxidation of alcohols result in formation of a carbon-oxygen double bond. So here what we'll see that oxidation can be defined in different ways. Here we will see oxidation as loss of hydrogen. Alright, so if you can see that this bond between carbon and oxygen has been broken, and this bond between oxygen and hydrogen has been broken. So we are removing hydrogen here and here, right? So we are removing two hydrogens and we are getting a carbon-carbon double bond, like that one, right? So loss of hydrogen is called oxidation. So here we'll consider the oxidation process, right? So alcohols, when they undergo oxidation, they form carbonyl compound. Right, these reactions are also called dehydrogenation. D means loss, hydrogenation means hydrogen, right? So since we are causing the loss of hydrogen, so that's why this oxidation reaction is also called dehydrogenation reaction, right? So depending on what you are using, which oxidizing agent you are using, you may convert primary alcohols into aldehyde, or you may also convert primary alcohols directly into carboxylic acids. So here we have primary alcohol. So under normal conditions, if you carry out the oxidation of primary alcohol, we get aldehyde, and this aldehyde is further oxidized into carboxylic acid, right? So in case of alcohol and aldehyde, you may say we have caused loss of two hydrogens, right? That's oxidation. But in case of carboxylic acid, we have added one more oxygen. So oxidation in this case will be considered as addition of oxygen. In that case, we consider this reaction as oxidation because we have caused the loss of hydrogen, right? And in this case, we have added one more oxygen, so that's why this reaction is called oxidation. Also, this reaction will be also called oxidation. So suppose that you want only to convert this alcohol into aldehyde, you don't want to convert it into further carboxylic acid, that we may use of chromic oxide, CrO3, right? If we have this alcohol, again we just want that to be converted into only aldehyde, right? We can use of pyridinium chlorochromate. So PCC stands for pyridinium chlorochromate, PCC, right? So in presence of PCC, you can only convert alcohol into aldehydes, so it cannot be further converted into carboxylic acid. However, if you have secondary alcohol and you are making use of chromic oxide, what we get is ketone. So ketone cannot be further converted into carboxylic acid, right? So you can convert primary alcohol into aldehyde, and aldehyde can be converted into carboxylic acid. But whenever you have a secondary alcohol do not get converted into carboxylic acid. It only gets converted into ketone. So tertiary alcohols do not undergo oxidation reaction, and when you are using very strong oxidizing agent like KMnO4 and you are using at high temperature, then different bonds of carbon and carbon will break, and what we'll get mixture of carboxylic acids. So if we have a tertiary alcohol, so we not get carboxylic acid, we will not get aldehyde, we will not get ketone. Otherwise what will happen, that all the carbon-carbon double bonds will break at different positions, and each fragment, each part that will be produced as a result of such cleavage, each part will be converted into carboxylic acid, right? So in case of tertiary alcohols, what we do under strong oxidizing conditions, under strong reaction conditions like KMnO4 or K2Cr2O7 at high temperatures, different carbon-carbon bond will be break and we'll get mixture of carboxylic acids containing a lesser number of carbon atoms. Okay, so next we have dehydrogenation reactions. Right, so when vapors of primary and secondary alcohols are passed over heated copper at 573 degrees C, 573 Kelvin, then dehydrogenation takes place. Again, dehydrogenation means loss of hydrogen. Right, so again, since it's loss of hydrogen, this is also called oxidation reaction. Right, so whenever dehydrogenation takes place, we can get an aldehyde or ketone, while tertiary alcohol will not undergo dehydrogenation, they will undergo dehydration. Right, so just compare these reactions. So we have copper in all cases and temperature is 573. In case if you are starting with primary alcohols, we get aldehydes. In case we are using secondary alcohols, we get ketones. But in case if we are using tertiary alcohol, we don't get aldehyde or ketone. What we get is the dehydration product. These are dehydrogenation. We are causing loss of hydrogen. But in this specific case, in case of tertiary alcohols, we get dehydration. We have caused loss of water. Right? So this is the difference in these reactions. Okay, so these were the reactions of alcohols, for example. But let's consider that we have reactions of phenols. Now we will be considering the reaction that will involve the benzene ring, right? So in case of phenols, the benzene ring is very electronically rich. Since benzene ring is electronically rich, means phenols are electronically rich, right? So these will always be attacked by electrophiles. So since phenols are electronically rich, these will be attacked by species which are electronically deficient. Now what happens that in case of phenols, the presence of hydroxy group, the hydroxy group will direct the incoming group either to ortho or para position. Why ortho and para position? Because the hydroxy group is electron donating, and this will create electronic density, higher electronic density at ortho and para positions. And the electrophile, since that's electronically deficient, that will prefer electronically rich positions. So फिनोल के केस में चूँकि इलेक्ट्रॉनिक डेंसिटी बहुत ज़्यादा होती है, तो फिनोल के केस में जो इनकमिंग ग्रुप होगा वो ऐसी पोजीशंस पे आएगा जहाँ इलेक्ट्रॉनिकली डेंसिटी ज़्यादा अवेलेबल है, क्योंकि खुद इलेक्ट्रोफाइल डेफिशिएंट है। फिनोल के केस में जो हाइड्रोक्सी ग्रुप है वो इलेक्ट्रॉनिक डेंसिटी को ऑर्थो और पोलर पोजीशन के ऊपर ज़्यादा इंक्रीज़ करता है। So as a result, phenols will direct the incoming groups at ortho and para position. So we will discuss different electrophilic substitution reactions. Firstly, nitration. Alright, so we have a phenol here and we have a nitro group. So nitro group is the electrophile. Alright, that electronically deficient species. Here you can say that in case of phenol, this nitro group is 1,2. It's having 1,2 relationship. This is ortho product. And in this specific case, the nitro group is having 1,4 relationship. This is the para product, right? So under these conditions, what we do is that we take a phenol and we make use of dilute nitric acid at low temperature. Then we get a mixture of ortho and para nitrophenols. And both of these isomers can be separated by steam distillation. Right, so how we can separate them? By means of steam distillation. For that you have to have basic concept about intramolecular and intermolecular hydrogen bonding, right? So orthonitrophenol is more volatile because it has intramolecular hydrogen bonding. You can say that this is hydrogen bonding within the same molecule. Because it is forming intramolecular hydrogen bonding, it's forming bonding within itself, it is not attracted by other molecules. So this molecule is behaving as if it is alone, and if a molecule is alone you can easily vaporize that. But in case of paranitrophenol, so paranitrophenol forms intermolecular hydrogen bonding, right? Because of intermolecular hydrogen bonding, the molecules become strongly associated. They don't break their bonding. So because of their association, they have stronger intermolecular force of attraction. You need higher energy to make them into vapor state, right? So a compound can be converted into vapor state once you have to break its intermolecular hydrogen bonding, right? If intermolecular hydrogen bonding are stronger, then in that case it becomes difficult for a compound to be evaporated. While whenever there is intramolecular hydrogen bonding, such compounds can be easily made volatile. So that's the reason why orthonitrophenol is more steam volatile, right? It can be easily volatilized and it can be easily separated, while paranitrophenol is less volatile because it is having intermolecular hydrogen bonding. right? So if you use concentrated nitric acid, so we say in the last slide that we made use of dilute nitric acid, but in case if you use concentrated nitric acid, then we get 2,4,6 trinitrophenol, right? This is called picric acid, right? So if you use concentrated nitric acid, you get nitro at all ortho and para position, but if you use the dilute nitric acid, you either get ortho or either get para product. Okay, so halogenation. You can add a halogen, you can place a halogen on the benzene ring. Again, the position on which this bromine will come will be at ortho or will be at para position, right? So on treating phenol with bromine, we get different products under different reaction conditions. So we'll consider the conditions under which we get different products. So when the reaction is carried out in solvents of lower polarity, non-polar solvents, such as we make use of CS2, carbon disulfide, and we make use of low temperature conditions, right? So in presence of non-polar solvents or solvents of lower polarity and at low temperature, so we get this as minor product, ortho as minor product, but the para product will be major product, right? So in case of phenol, we don't need any catalyst, right? We don't make use of any Lewis acid. Why is that? So because the bromine molecule can take place, polarization of bromine molecule can easily take place in the absence of Lewis acid, right? Why is that? So because this phenol is highly electronically rich, it can easily attack this bromine, right? So there is no need to use any Lewis acid for reaction to work. Alright, so when we make use of bromine water instead of simple bromine, then we get 2,4,6 tribromophenol, right? So usually the hydrogenation of benzene takes place. Halogenation of benzene takes place in presence of Lewis acid such as FeBr3, right, which polarizes the halogen molecule. But in case of phenol, we don't need to make use of this FeBr3 because this phenol is active itself. It's very reactive, so it don't require any Lewis acid. Next is Kolb's reaction, right? So we have seen in previous slides that the phenol, when it reacts with sodium hydroxide or sodium metal, it forms sodium phenoxide, right? So phenoxide is very, very reactive, and what happens that when it is reacted with carbon dioxide, so this carbon dioxide is electrophile, that's electronically deficient. So this phenoxide will attack on this carbon dioxide and result in formation of this carboxylic acid, which is salicylic acid. An interesting thing is that the major product of this reaction is ortho product. Okay, so the para product if formed is very, very low concentration. It's not formed at all. So this reaction, this specifically yields this 2-hydroxybenzoic acid, and this 2-hydroxybenzoic acid is commonly known as salicylic acid. Okay, so another important reaction which phenols undergo is Riemann-Tiemann reaction, right? So reactions will involve treating phenol with chloroform. The CHCl3 is called chloroform in presence of sodium hydroxide, right? So by means of this reaction, what we get? We can have an aldehyde group at ortho position. So in the previous reaction, in the Kolb's reaction, we got carboxylic acid at the ortho position. But by means of Riemann-Tiemann reaction, we can have an aldehyde at ortho position. What happens is that when we react this phenol with chloroform and sodium hydroxide, so now we are using sodium hydroxide in aqueous solution, so we get an intermediate which is substituted benzyl chloride. So this is substituted benzyl chloride, right? So this substituted benzyl chloride in presence of sodium hydroxide is converted firstly into this aldehyde group, and then we have phenoxide here. So in order to remove this phenoxide and convert it into phenol, we add acid to it, right? So upon acidification, upon addition of acid, this is converted into alcohol, into phenol, sorry. So this 2-hydroxybenzaldehyde is called salicylaldehyde. So cold electrolysis yield salicylic acid, while Riemann-Tiemann reaction yields salicylaldehyde. Okay, so reaction of phenol with zinc, right? In such case is the only way in which we can break the bond between carbon and oxygen, right? Otherwise phenols don't undergo carbon and oxygen bond cleavage. So only way you can cleave the carbon oxygen bond of the phenol is by reacting this with zinc dust, right? So overall reaction is loss of oxygen. So oxygen is lost, zinc is converted into zinc oxide. So if you want to convert phenol into benzene, this is a simple way, just treatment of phenol with zinc, and there you go. Right, so if you have to convert phenol, if you have to oxidize phenol, then what we can get, we make use of chromic acid, right? Chromic acid does not exist as such. We have to make chromic acid. So we can use simply chromic acid by reacting sodium chromate, Na2Cr2O7, with sulfuric acid. You can also make use of potassium dichromate, or you may use of sodium dichromate, right? So these reaction of sodium dichromate or potassium dichromate with sulfuric acid will result in formation of chromic acid. So chromic acid cannot be stored as such, so you have to prepare whenever you have to use it. So when we treat this phenol with chromic acid, what we get is benzoquinone, right? So we have carried out an addition of OH here. So in presence of air, phenols also undergo slow oxidation to form quinones, but the reaction is very slow. But if you have to make the reaction very rapid, just make use of chromic acid, right? Okay, so here's the quiz for this course. You have to classify the following as primary, secondary, and tertiary alcohols, right? And also you have to define which of these will be strongest acid. Assignment will be included with this lecture as well. So here's the recommended book. Thank you.